Okay, the point of this video is to see just one more example of a chi-squared goodness of fit test. We're going to start at the beginning, go all the way through all 4 steps, just so that you can see it all together. So first of all, why don't you pause the video, take a moment, and read this scenario. So this first sentence is telling us, just according to the US Census, here's the percent of people in each age category. And then the table is showing us a sample. The sample was gathered by randomly dialing landlines and just seeing who answered. So of the 1,048 landlines they called, 148 of the people who picked up were in the 20 to 29 category, 186 were in their 30s, etc. So the question is, do these data provide convincing evidence that the age distribution of people who answer their phones is not the same as the distribution of all US residents? So we're comparing 2 distributions, just like in the M&M example. In the M&M example, the 2 distributions were the distribution of colors claimed by Mars and the distribution of colors in our bag. Here, the 2 distributions are the distribution of ages for all US citizens versus the distribution of ages for people who answered their phones. We're going to see if they're the same. Now, I did not really leave you enough room on the right there to find the expected counts, so I'm just going to make a new version of the table. Here's each age group and the observed counts. And what we're going to do is find the expected counts. So what you have to do for that is look back at the problem. 19.1% of US citizens are in their 20s. So we take 1,048, which was the total number of people they called, multiply it by 0.191. We would expect 200.168 of the calls to be answered by 20 to 29-year-olds. So why don't you pause the video and find the other 4 expected values now. Alright, so those are our expected counts, and right away I can see that way fewer 20-year-olds answered than we expected. Way more 50-year-olds answered. 60 plus is pretty close. 40 to 49 is very, very close. 30s, not too bad. So there's a couple that are very different and one that's almost exactly the same. Now for our state step, our null is going to be that the age distribution of people who answer their phones is the same as the age distribution of all US residents. Our alternate will be that they are different. And let's test at 0.05. I didn't write that here, but we're going to go with 0.05. For our plan step, there were 3 conditions to check for chi-squared goodness of fit. The first was that we had a random sample, and we did have that here. It said it was a random sample. The second was expected counts. All expected counts have to be greater than 5, and they are definitely greater than 5 here. We calculated them all. You don't have to show them again if you've showed them somewhere else in your work. You can just say see above. And then the last thing was independence. We're sampling without replacement, but there are definitely more than 10,480 Americans. That was 10 times sample size. So all of our conditions are met, which means we can do the chi-square goodness of fit test. And yes, please say goodness of fit. There are actually 2 other types of chi-squared tests. Spoiler, we'll do them in the next video. So it is important that you say goodness of fit or GOF. All right, for the do step, we need to calculate chi-squared, which, like I mentioned in the M&M example, you need to show your work for at least 1 component. Honestly, if you just show the first one, that's fine with me. But we're doing observed minus expected squared over expected. This is on the formula sheet. It's on the very front page, so you don't have to memorize it. And I'm just getting those values from here. Observed minus expected squared over expected. We do all that work, which I did on my calculator, and if you want to just trust me, that's fine. 48.2. That's very big. Remember that the chi-squared distribution looks like this. It is very skewed right. If we get a large chi-squared value, that means our expected counts were very different than our observed counts. So a large chi-squared value means that there were lots of components of our distributions that were different. 48.2 is very large, so that's why I drew it all the way over here. Our p-value is going to be the area to the right of our chi-squared, because we are only interested in our chi-squared or something more extreme. More extreme with chi-squared is always to the right. Never left-tailed, never two-tailed, it's always right-tailed. So we can calculate our p-value. You're going to use chi-squared CDF, lowers 48.2, uppers 1,000. Degree of freedom is the number of categories minus 1. So We have 20s, 30s, 40s, 50s, 60s. That's 5 categories. So we're using 4 as our degree of freedom. Okay, but anyway, when you type it in, you get 0, or roughly 0, which is a very small p-value. So time to conclude. The probability of getting this chi-square value, or something larger if the null were true, is about 0. Notice I said, or something larger. You could say, or something more extreme. We're not going the other direction, so I said larger. It's nearly impossible for this to happen, so we will reject the null and conclude that the age distributions of people who answer landlines and all US adults are different. Notice that I included context. I didn't just say the distributions are different. I included context about what those distributions are. And then the very last thing you should do, if you reject the null, you should probably state which parts of the distributions were most different. So the groups with the largest components of chi-squared were the 20s and the 50s. Fewer 20s answered than expected, and more 50s answered than expected. So I could even add another sentence here when I say, like, young people are less likely to answer landlines, and old people are more likely to answer landlines. It's probably less that people in their 20s don't answer their landlines, it's more that people in their 20s don't have landlines. I don't even answer my cell phone unless I see that it's my mom, so I definitely wouldn't answer a landline if I had one.